Okay, so from now on, let's study and let's take a look at some basic definitions to before diving into some more great details on the physics of BJT. So on the top left hand side, you may see the cross-sectional view of P and P BJT. So the name of P plus, the left hand side of P region, is named as emitter, and the region in the middle or in between emitter P and another P is base, and its type is n-type. And on the right hand side, the P region is named as collector. Okay, so think about how come the previous researchers has used this name: emitter, base, collector. Why emitter? Why collector? Why base? Now, for a given voltage difference between first P plus N junction, and maybe we should apply another amount of voltage difference between this second NP junction or second PN junction. Anyhow, you can clearly see that there are two different PN junctions. So by combining those two PN junctions, we can build up the single BJT device. And how come? Why we are using this name: emitter, collector, and base? Well, my answer is this: emitter means something, right? Something which can emit out, which can output its own carriers. But this is a p-type material, so majority carrier of it is holes. So hole H plus may be emitted out away from this emitter. What about this guy, collector? Collector is the thing which can collect, which can catch and grab and get those carriers coming from emitter. Okay, so the hole would be arrived at the collector region like this. So base means the base station and basement of your apartment or your house. Base means kind of fundamental or kind of center things, right? So in between emitter and collector, the reason could play the role of base. Okay, so in that sense, you can figure out how those three different names, emitter, base, collectors, are originated. Okay, all right. And then with your own knowledge on PN junction diode, how to inject or how to emit out the holes from P plus region. How to do that? Yes, you should apply forward bias in between emitter and base. Then many holes would be injected into the n-type region, which is base, and those holes would be moved forward. How to move? Drift or diffusion or recombination or else? Yes, diffusion, as we have learned. These minority carriers can be diffused within the base region or within n-type region. But as we have learned, what if this physical length of base is very small and short and narrow? Then you may have already a chance to study by yourself the narrow base p-n junction diode. Okay, so what if this physical width of base is even shorter than a single diffusion length of the holes injected from the emitter? Then what would be happened? As we have learned, the excess hole concentration in this base, instead of n, previously there are only two types, p or n, but now we have three different regions. So if I'm saying n region, well, in this PMP BJT, n should be indicate base only, but that's okay. However, what if I'm talking about delta n sub p, that this p indicates collector or emitter? That's very confusing. So from now on, when when it comes to the BJT, this subscript indicates the reason, one of the three reasons in BJT. Okay, so here delta P, P sub B indicates excess hole concentration in the base. Okay, so in the base, what if the physical width of base is shorter than a single diffusion length of holes injected from emitter? Then delta P sub B would be written with a first order polynomial equation. I mean the linear function of x along the x direction. Then many of holes would be survived well in this base region, and they're gonna be delivered, finally arrived into the collector region. So once holes are well arrived in the collector region, then this H plus hole is a majority carrier in this p-type collector. Then they are well collected and they well grabbed into the collector region, the second p-type region. Then we can say that the hole has initiated and started to run throughout base and into the collector. Then we can say that the current has been formed from emitter to collector. Okay, so that is a kind of a main function and how the current can be formed and flown throughout the PNP BJT device. So we're gonna study that more later. Anyhow, right now, please be familiar with those new words: emitter, base, collector. And now we're gonna keep our eyes on P plus and P BJT first. Later on, we're gonna study the MPN as well. But now, please keep an eye on P and P device. Okay. So as described here, BJT bipolar junction transistor is basically three-terminal device. PN diode is basically a two-terminal device, right? Plus minus two terminals. That's it. There is no other terminals available in this PN diode. However, take a look at this PNP BJT. How many terminals or how many electrodes can we make? Can we paste on this BJT? Yeah, one, two, three. So basically, BJT has three terminals: emitter terminal, base terminal, collector terminal. So instead of drawing the cross-sectional view of PNP BJT, let's adopt a circuit symbol for BJT. So that node is emitter, this node indicates collector node, this node indicates base node. And using this arrow, banded arrow and banded solid line and another straight line. So let me write down it here: base, emitter, collector. So that is emitter, collector, and base. So this arrow indicates uh, the type of BJT. If this arrow indicates toward the base side, then this a PNP BJT. In case of NPN BJT, we're gonna use this circuit symbol: base, emitter, no, collector, emitter, and in this direction the arrow can be placed. So this circuit symbol indicates NPN BJT, and that circuit symbol indicates the circuit symbol for PNP BJT. In my lecture, I'm going to give you some more great details on a PNP BJT because it's much easier and it's a much simple version of extended PN diode. Okay, so one more definition is this, and that. But that's very simple. Emitter, voltage difference between emitter and collector is denoted as V sub VC, emitter base, V sub EB, VCB indicates voltage difference between collector and base. Okay, this is very simple and straightforward. And if I write down V sub EB with another equation, that means VE minus VB. So the first one, second one, okay? First one and second one. So please repeat it for V sub CB and V sub EC. And one more thing is, if you would like to know the voltage difference with respect to base, then the answer can be like this: VE minus VB plus VB minus VC, and this guy would be minus VC minus VB. So that this VE minus VB means voltage difference between emitter to base. So you can write down it VEB. And this guy VB minus VC is identical to minus VC minus VB. So this voltage difference between collector and base is VCB, collector base. So don't forget this minus. So this minus is here and VCB is here. Okay, so simply speaking, if you'd like to know the voltage difference with respect to a certain voltage, certain electrode, then simply plug in here, and that's very simple. Okay, so on the right hand side, uh, you may understand it by yourself. It's very simple, right? So that is, base to emitter. Just take a look at the direction of this arrow. So you may catch that this circuit symbol indicates NPN BJT, and the voltage difference between collector to emitter. So collector to emitter, plus minus, okay? So the first letter indicates plus electrode, the second letter indicates a minus electrode. So VBE means a base to emitter, base to emitter voltage. Okay, so V sub BE, and that is base to collector, so base to collector. Okay, so this voltage difference between base and collector. All right, so I hope you all to simply understand and write down the voltage difference between two terminals in three-terminal device. Okay. And now let's take a look at how to define the current flow in this PMP or NPN BJT device. So here IE, IB, and IC. So emitter current, collector current, and that is base current. So emitter current should be equal to the base current plus collector current. Why is that? It's a kind of Kirchhoff current law. The total amount of current input should be equal to the total amount of current output. So for this node, the input current is I sub E, emitter current, and the output current, we have two different output current, IB and IC. So by summing up those two output currents, uh, should be identical, should be equal to the input current, which is I sub E. Okay, so remember this one. But one notice for that is this: the current flow sign convention used in our textbook, BRS book, is not well aligned. It's not well to follow the IEEE convention. So do not say IEEE. No, 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 no. That's not allowed. IEEE. Okay. So IEEE convention. Okay. So basically, IEEE convention is a kind of standard. However, the BRS book did not follow the IEEE convention because because this current flow sign convention is much straightforward, easy to understand. So uh, I'm not a big fan of BRS, but anyhow, his current flow sign convention used in BJT is makes sense more. So I'm going to use it. So emitter current is equal to the base current plus collector current. So think about this and memorize it. And what about the NPN BJT? Now, herein, collector current is an input current, and there are two, no, 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 one more. Yeah, IC and IB is an input current, okay? And IE is a output current. Okay, so you can build up this equation by using Kirchhoff current law. All right, that's all for the BJT types. Two types, PNP and NPN, and the voltage definitions for voltage and definitions for current component in BJT. All right. Okay, so I guess you should have your own time to practice the definitions of voltage and current in BJT and have your own have yourself to be very familiar with circuit symbols for NPN and PNP BJT. Okay, so please have your own time and see you in the next movie clip. Thanks. Bye bye.